Ah, well, hello there. Come on, internet. There we go. Come on, computer, do your thing. There we go. Good, good, and good. All right. I'm gonna get started in about a minute. Just setting some things up for myself. I got my coffee. I got my paper. Trying to make it feel as at home as possible in my classroom. I'm actually going to be allowed to go back to my classroom on Monday for a very brief amount of time to get any stuff I may have left there. It's going to be fun, mainly for me. Let's see here. Checking the email. Okay. So the way that I am gonna break this up into is I'm going to break it up by section in the textbook, which we covered most of the sections. In fact, in chapter 8, there was only one section that I purposefully skipped. I didn't find it particularly necessary. But we'll go through it a piece at a time. So after this video is done, in the timestamps I will put the codes in, and we'll figure that out. Oh, my rubber band broke. Well, that's just great. I have a rubber band holding my phone in place, and it legitimately just broke. And there goes everybody. That's what happens. Everybody ends up falling. Well, that was fun. Let's see if I can't fix this. There we go. That's what happens when I'm working with homemade stuff. There we go. That should work. But I am going to be putting the timestamps in after the fact, so people can go and watch whatever they need to watch. And I will put titles of certain things at the top of the page as well. So let's start very simply. In our textbook, this was section 8.1. This was multiplying and dividing rational functions. I'll just put multiplying and dividing rationals, and that'll be the reference that I have for myself. Now, in this particular section, everything was just being multiplied and divided, and you had to cancel things out using that multiplication and division property that we have done forever, basically. Whenever you have something divided by itself, it cancels itself out. So, for example, there was a problem like this. Now, you may not have seen these problems before, but that is perfectly acceptable. Let's just see what we can do with this one. There we go. Negative 16xy over 27z times 15z cubed over 8x squared. Now, everything's being multiplied and divided. There's nothing that can actually be factored here. See, typically when we go about trying to factor something, we're looking at a binomial or a trinomial that can be factored using the Tucker method, let's say. And yes, even though we do have, oh look, there's a quadratic, it's an 8x squared, that can't be factored. Technically already is a factor unto itself. So with this type of problem, we would just look about what we can simplify, what we can cancel. Piece at a time, you could see a negative 16 and a positive 8 that are being forced into a fraction together. Negative 16 on top, positive 8 on bottom. Again, everything's being separated by multiplication division. This would become a negative 2, and this would just cancel out completely. You can do the same thing with the 15 and the 27, except with a different number. The 15 and the 27 are both divisible by 3. Think of them as their own little fraction, 15 over 27. Divide that by 3, divide that by 3. In terms of the coefficients, the numbers on the front of the variable, they're done for now. They're done for now. There's nothing else we can do with them. You might be able to say, oh, well, could anything simplify with the negative 2 and the 9? Well, no, they can't. We have the variables to deal with. If it helps, you can bring everything over to the right, and it may help in terms of a visualization. If you just look across the top of the fraction, we have a negative 2xy, 5z cubed. Everything's being multiplied, so this is a negative 10 xy z cubed. On the bottom, again multiplying across, there's the 9 still. Now, yes, zx squared, but I'm going to write it as x squared z, just for the sake of alphabetical order. Clearly, the negative 10 and the 9 have nothing in common. Nothing can simplify from there. But something can happen with these x's, and something can happen with these z's. On the top of the fraction, yes, it is just an x to the first power. On the bottom of the fraction, it is an x times x. It's an x squared. This top x will cancel out with one of those x's on the bottom. You could also think of it as, well, the top only had an x to the first, the bottom had an x to the second, the bottom wins by 1, or some junk like that. That's one of the ways that I described it in the original lesson. You can also look at the z's. If you look at the z's, there's the z cubed on top. That's z times z times z. And there's a z to the first on bottom. The z to the first on bottom will cancel out one of the z's on top, leaving 2 of them. The resulting answer, negative 10y z squared now, over 9x. These were what we called monomial problems. These monomial problems didn't have to use the Tucker method or anything like that. They were just simplified as is, everything being separated by multiplication division. Let's look at another example. This one's gonna not dive off the deep end, but it's gonna be kind of nice. X squared minus 2x minus 8 over x squared plus x minus 12. Now, I'm adding in the parentheses myself. In the original problem that's in the textbook, there are no parentheses. Times, parentheses, x squared plus 2x minus 15 over x squared plus 7x plus 10. Again, when you see these on a page, when you see these on an assessment, most likely the parentheses will not be there. I add them in simply because I know that they're there, and it helps conceptualize the problem. Now you have trinomials. And these trinomials can be factored using the Tucker method. Now, not to go into great detail with the Tucker method, because that was a separate lesson unto itself. Each of these should be able to be factored. Should be. I know they are, but the key is that sometimes you might be faced with an issue. Let's just look at it a piece at a time. Let's look at the top left. In the top left, you're trying to find two numbers that multiply to -8 and add up to -2. Looks like -6. No, not -6. I'm sorry. -4 and +2. Yep, that works. -4 and +2. They got to multiply to -8. They have to add up to -2. Nice. Let's go bottom left. In the bottom left, two numbers that multiply to -12 and add up to +1. We're looking at x plus 4, x minus 3. These two terms do not cancel each other out. They don't. They are not the same thing. They don't cancel each other out. Nothing does so far. Let's look at the top right. In the top right, I'm looking at something like +5 and -3. At this point, yes, you do see something that cancels out. I'll deal with that in a moment. Let's just deal with the bottom right. The bottom right, I'm looking at +5 and +2. Multiply to 10, add up to 7. Now stuff can start to cancel out. Everything's being separated by multiplication division. In this section, in 8.1, if it was separated by multiplication division, then you could begin canceling junk out like that. So, x minus 3's, they cancel. One on top, one on bottom, 1 for 1. The x plus 2's, they cancel, 1 for 1. The x plus 5's, they cancel, 1 for 1. Leaving you with x minus 4 over x plus 4. And they do not cancel anything else. You might want to try and be like, oh, x over x and 4 over 4 and some junk like that, but that will not do it. You have to assume that there are parentheses around the top and the bottom of this problem. And because of that, nothing else cancels, because the top does not match the bottom. Let's try another one, a little more, not extreme. I shouldn't say extreme. Extreme is the wrong word. Extreme is definitely the wrong word for what I want to do. Let's see what we got here. There we go. I'm going to try a couple more from this section before I move on to 8.2. Let's look at something like x plus y over 15x divided by x squared minus y squared over 3x squared. Now this one is a little bit more extreme. Just a tad bit more. With this problem, yes, you're not used to seeing it as x squared minus y squared. We're not used to seeing it with multiple variables there. But this one can be factored into x minus y, x plus y, just like every difference of two squares that we've seen. In the first fraction, nothing can factor. I would like to, as we typically do, keep change flip. And when we keep change flip, this becomes 3x squared. And the x squared minus y squared, as I said, becomes x minus y, x plus y. I don't know why I just wrote a 2 there, but that's a y. Very strange. Now, there we go. I was just checking something on the computer. The x plus y's definitely cancel. The 3 and the 15 simplify to become a 1 over 5. You don't have to write the 1. You can if you want, but the 1 doesn't matter because it's being multiplied, and multiplying by 1 doesn't do anything. There's an x squared on top and an x to the first on bottom. As a result, well, the x on the bottom cancels. It only cancels out with one of the x's on the top. What we're left with on the top of this answer is just an x, and on the bottom we're left with a 5 times x minus y. You can distribute that 5 if you want to, but it's not necessary. You don't have to. You can leave it just like that. Last example for this section, because I would like to talk about the other sections that you have in store. Here's a little bit of a challenge problem for this particular section. I say challenge because I like it. And typically the problems that I like are the ones that people freak out at. Now the parentheses are not in the original problem, but I'm adding them in for the sake of simplicity. There we go. It is not as bad as it looks. This larger division bar in the middle separates the whole problem. And what ends up happening, and I'm writing this in red so you can see it, what this problem is really saying is this large fraction divided by this large fraction. This problem is the same as this problem with this large division symbol in the middle. And I'm going to do a little keep, change, flip action in order to save myself some space in a moment. It's going to be some kind of a fraction times some kind of a fraction, which I'll deal with. I'm going to do a lot of things all at once. This first fraction is still going to remain in the same order here, except I do have to factor the top of that fraction. When I factor the top of that fraction, it should become x plus 6, x minus 3. Two numbers that multiply to negative 18 add up to positive 3. And the bottom stays in x plus 4. This top fraction is what this fraction becomes. Now, like I said, I am going to do a little keep, change, flip action going on here. Keep, change, flip. So the top of this fraction is now an x plus 4. The bottom of this fraction is going to be whatever this quadratic, this x squared plus 7x plus 6 should become, which is an x plus 1, x plus 6. They multiply to 6 to add up to 7. Once you have it here at multiplication, you can begin canceling things out the way that we normally do. X plus 4's cancel. The x plus 6's cancel. And we're left with an x minus 3 on top and an x plus 1 on bottom. Again, I can't cancel those x's in the final fraction because they don't. It has the properties of an x minus 3. The bottom have the properties of x plus 1. They are not the same term. They're not the same factors. In order for the factors to cancel, they have to be exactly the same. 8.1 was all about multiplication division. 8.2 was all about addition, subtraction. Let me give you an example. So this was 8.2. Add, subtract, rationals. Nine over 4ab plus 5a over 6b squared. Now, the directions would say something to the effect of simplify. And yeah, you're not solving for anything, you're just simplifying. But in order to simplify, you have to bring these two fractions together into a single fraction. That single fraction needs to have a common denominator. Now, the denominators, there's a 4ab and there's a 6b squared. Well, let's go through it a piece at a time. Let's start with the constants, or the coefficients. This one has a 4, this one has a 6. Least common multiple is 12. In order to make that a 12 so that they match each other, I would need to multiply this top fraction by 3 over 3. I am not changing the value of that first fraction. I'm just simply changing the way that it looks in order to force a common denominator. In order to make the second fraction a 12, I would have to multiply it by 2 over 2. Again, multiplying it by 1 doesn't change the value. That takes care of the 4 and the 6. Let's talk about the variables. This first fraction has an a on the bottom. The second fraction does not. So, in order to force it, I'm going to multiply that second fraction by an a over a. Because then the bottom of the fraction would have the variable of a that the first one originally started with. Now, the b, they both have a b, but this one is a b squared. In order for them to have common denominators, they need to have exactly the same denominator. In order to do so, I am going to have to multiply that first fraction by b over b. That would force it to be b squared. Again, look at the bottom of each fraction now. On the first fraction, I'd get a 12a b squared. On the second fraction, I'd have a 12a b squared. That's what I wanted. But as a result, the top of my fraction is going to change because I had to do that multiplication. The first term would simply become a 27b, and the second term plus would become a 10a squared. It looks terrible, but this is the answer. That's what they wanted. Nothing else can simplify. Whenever you do adding and subtracting problems, you should always double check to make sure that the top and bottom don't simplify farther. And the only way that you're going to be able to do that is if you tried to factor the top of the fraction. Now, in this case, the top of the fraction cannot factor, can't do anything with it. So I'm going to have to leave it as is. Let's look at another one. That's a nice one. Yeah, let's do that one. Let's do that one. So I'm looking at 3 over 4x minus 8 minus x minus 1 over x squared minus 4. Again, with this problem, the original did not have these parentheses. The original did not have these parentheses. I added them in. Makes my life a lot easier to add them in. I'm going to have to factor here first, actually. Before I do anything else, I'm going to have to factor. On the bottom left, I can factor out of 4. On the bottom right, I can turn this into an x minus 2, x plus 2. Once I've done stuff like that, then I can begin to try and see, okay, what is each denominator missing? In the second fraction, The denominator's clearly missing a 4. I'm going to have to multiply the top and bottom of that by 4. And I'm writing that in red so you can see the discrepancy between the two. Now, when I eventually distribute that number, you got to keep in mind that that's a -4 that I'm going to be distributing. In the first fraction, I'm clearly missing an x plus 2. I'm going to have to multiply the top and bottom by an x plus 2. So, I got to simplify this junk out. The denominator would now be a 4, an x minus 2, and an x plus 2. I'm going to leave that as is. I'm not going to multiply that back out. Why would I? But the top, mind you, that's a -4. The top would become a 3x plus 6 minus 4x plus 4. Let's just see what happens now. That actually becomes what? A -x plus 10. That's weird. -x plus 10 over 4x minus 2, x plus 2. The top of that fraction cannot factor any farther. You must always double check to see if you can factor farther. But since it can't factor, we're done. That is what the answer would end up being. Let's try one more adding and subtracting. And then I want to get to the really big issue of this chapter, which was graphing. I love me some graphing. But let's try another adding and subtracting problem. 3 over 3x squared plus 2x minus 8 plus 4x over 2x squared plus 6x plus 4. Now, again, with this problem, you have to assume parentheses around the tops and bottoms. It helps with trying to, what's the word I'm looking for? It helps when it just visualizing, conceptualizing what the problem should actually be. Now, you could do a little bit of the Tucker method off to the side. You're going to have to for both of these. But let's just pretend that I actually did that. Let's pretend that I actually did the Tucker method already. Sorry, I'm clicking something right now. There we go. So if I did that, 3 over, which, by the way, you should always double check to see if you can do a GCF first. Always double check the GCF. I'm going to try and do something in my head right now. -24, two numbers, 6 and 4. The 4 is negative. So this should be -4, and this should be +2. Yeah, that works. Double checking, double checking, double checking. Yeah, that works. And then over here, we get a 4x. Should be a 4 and a 1, I believe. No, that doesn't work. That does not work. Oh, that's why. I completely violated the rule that I said before. I completely violated the rule that I said I should do, which was make sure I double check to take out a GCF. If I take out a GCF, my life becomes a lot easier, because now this becomes an x plus 2 and an x plus 1. Goodness gracious. So, I'm looking at this problem. They both have an x plus 2 in common. Where's my red pen? There it is. They both have an x plus 2 in common, so I don't have to worry about that. This first one is missing both a 2 and an x plus 1. This second one is missing 3x minus 4. There's a knock at my door. Hold on.
Sorry.
Should announce that. Sorry for the disruption. Let's see what happens now. Basically, again, you have to look at what the denominators are missing. They both had the x plus 2. This one didn't have an x plus 1, and it didn't have that constant of 2. This one was missing 3x minus 4. Your denominators, again, you don't have to multiply out your denominators at all. You can leave your denominators as is. It's going to be this monstrosity that we have here. You don't have to worry about multiplying them back out. Leave it as is. The first fraction would become a 6x plus 6, because 3 times 2, and then distribute the 6, plus, you got to distribute a 4x, a 12x squared minus 16x. Oof, this thing. Let's just see what happens. The denominator, again, is going to remain the same. The numerator, 12x squared, oof, minus 10x plus 6. Man, let's see if we can factor that. Take a 2 out. Becomes a 6x squared minus 5x plus 3. Can that be factored? Let's see if it can be factored. Because if it can't be factored, then we're done. So I'm going to double check a discriminant here. B squared minus 4ac. Oh, that thing can be factored. So we're not done. Interesting. Did I get the right one here? Oh, no, I totally didn't do the 4ac. Yeah. 4ac. Yeah, totally. Cannot factor that. The only way that would be factorable is if the discriminant was a positive perfect square. So we are done. That's all we can do. It looks terrible, but that is what the answer is. Let's talk about graphing. Now, graphing these rational functions ends up being an interesting task. The reason is because of how much detail goes into it. Kind of crazy. Let's start with a basic problem. So hold on, this is 8.3 and 8.4 I combined into a single lesson. Just call them graphing rationals. There we go. There were two types of rational functions. There were the basic ones and the non-basic ones. So I am going to break this up into two parts. Here's a basic example. F of x equals 7 over x minus 2 plus 3. You can typically identify the basic examples when there is a linear function in the bottom of that fraction. Which in this case, yeah, there's an x minus 2 in the bottom of the fraction. The plus 3 is going to shift that whole thing up 3 units. The entire image is going to shift it up 3 units. The x minus 2 is going to determine where the vertical asymptote is going to be. For these problems, for the basic rational functions, Your horizontal asymptote typically starts out as y equals 0, but it will shift wherever the k value is. In this case, and I'll write this up here, f of x equals a over x minus h plus k. That plus k is going to be your horizontal asymptote, in this case 3. Your vertical asymptote, you take the bottom of the fraction, set it equal to 0, and solve. X minus 2, set it equal to 0. You get a vertical asymptote there. Now, whether it be with a graphing calculator, whether it be using Desmos, or whatever function you typically have, let me reset this thing. A table of values can be got through an electronic means. And notice when I type this thing in, the x minus 2 is in its own little set of parentheses. You're going to want to find some ordered pairs to the left and to the right of where that vertical asymptote is. And if you notice the vertical asymptote, there's an error. And I'm going to compare this against what the graph actually looks like. You don't have to get those 3 points. I'm just writing down everything that I see right here. And if you notice, I did not write down the vertical asymptote right in the middle. There was no need to do 2, error. Now this thing looks like it's been shifted up 3 units, so I'm going to focus heavily on the top 2 quadrants. -1.67, 0, and -0.5, 1, and -4. Ugh, I ran out of space already. Whatever. I actually can deal with that. Absolutely. Notice the dotted line. That is my asymptote. Nope. Forgot to put in my horizontal asymptote. I'll walk through what procedure you could have done after this. Yeah, I'm way going to run out of room here. I'm not actually going to graph 3, 10 then. See, 6.5. 5 and 1, 2, 3, 4, 5.3. There we go. There we go. I'm going to compare this to my graphing calculator in a moment. What we should be doing with these problems is this. You need to identify your asymptotes, see if there are any holes if need be, but that's for your non-basic ones. For these, it's just identify the asymptotes. The k value is your vertical. Set the bottom equal to 0, solve, you get your horizontal. Find a table of values. Plot those asymptotes by dotted lines. Plot the ordered pairs, draw your curves. Again, if you had a graphing function or a graphing calculator or something to that effect, you can see exactly what we got there. Let's try another basic one. One more basic one before I talk about the non-basic ones, because the non-basic ones are so much fun. In my opinion, of course, but they're fantastic. Here's another basic example. Graphing. Could be y equals, could be f of x equals. Does not matter. -4 over x plus 4 minus 8. There we go. So the procedure that I usually follow is this. Number 1, identify, because it's basic, identify your vertical asymptote. Your vertical asymptote, vertical asymptote, horizontal asymptote, y equals -8. Hoy vux, H-O-Y, V-U-X, H, horizontal, O, 0 slope, y equals in the equation. But it's whatever the k value is. Your vertical asymptote, x equals, you set the bottom of the fraction equal to 0 and solve. You get x equals -4. table of values. Again, you can get a table of values from Desmos. You can get a table of values from whatever graphing calculator utility you have. But you want to find, you can't even see it, there's a glare. There we go. You want to find a few points to the left. You want to find a few points to the right. Make sure you put parentheses around the bottom. There we go. Now, those numbers are quite large, but that's okay. We'll deal with that. This thing has been shifted down 8 units, so we're going to have to deal with that. This time, I'm only going to find a couple of points here. -6, -6, -5, -4, -3, -12, -2, -10. That should be sufficient for what I want to do here. Now, these are larger negative numbers, so I am going to be doing one of these to get those larger negative numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. And 1, 2, 3, 4, 5, 6. Perfect. 11, 10, 9, 8. There is my horizontal. -4. There is my vertical. Now I'm going to plot some points here. -6, -6. -5, -4. There we go. And you can see it's going to curve up and curve out with the horizontal. -3, -12. -2, -10. It's going to curve with the horizontal. It's going to curve with the vertical. And again, I'm going to compare this to the calculator in a moment. Now, the calculator is going to have part of this cut off because it only goes to -10 in each direction. So you can see that's a little cut off. Let me change my minimum here to -20. And we can see a much better view of what this thing is supposed to look like. There it is. But that's what we have to do. Identify your asymptotes, table of values, plot everything out. Now, when we talk about non-basic, the non-basic ones are going to be a bit grungier, to say the least. Non-basic. Let's start with, yeah, let's do that one. We'll start with this one. F of x equals 3 over x squared plus 4x. With these problems, first step, factor. First step is to factor. First step is to always factor if you can factor. In fact, this problem, you can take out a greatest common factor of x. Check to see if there are any holes. If anything cancels out, you may potentially have a hole. If something were to cancel out, you take whatever canceled, set it equal to 0, and solve. Nothing did here, so there's no holes. So I could even say no holes because nothing canceled. Okay. Now, with non-basic, the vertical asymptote is still the same. You set the bottom of the fraction equal to 0 and solve. Because of this, you actually end up with 2 vertical asymptotes. It's really weird, but you actually end up with 2 vertical asymptotes. Horizontal asymptotes are a little bit different now. With the non-basic, you take the leading term of the top of the fraction and divide it by the leading term of the bottom of the fraction. Now, if you notice here, nothing simplifies. Your horizontal asymptote is going to be whatever the horizontal asymptote would be of this particular graph, or whatever this graph is supposed to look like. It's really strange here, but the general idea is that this one's y equals 0. Typically, it's not going to be y equals 0. Typically, it's going to be y equal to a different number, positive or negative, or y equal to a slant. But in this case, 3 over x squared, it's just going to be y equals 0. Anything with a variable that's larger on the bottom will end up being y equals 0 for the horizontal. You could check for x-intercepts if you want to, but you don't have to. In fact, this particular problem will not actually have any x-intercepts. It's the top of the fraction equal to 0. But I'm fairly confident that we can go ahead and actually try and get a table of values going. Make sure you put the bottom of that fraction in its own little set of parentheses. Now there are two, you can see them right there, two errors. Those are your two vertical asymptotes. A hole will also show up as an error, but we have no holes for this problem. You just need a few points to the left and a few points to the right of each error. When I say a few, I just mean literally a couple. It also gives you a feel as to where you should be creating your axes. There we go. So I got a lot of smaller numbers. And I'm going from -6 to +2. There we go. Let's see here. Let's make that 1 and then that -1. That'll work. And then I'll go 1, 2, and then 1, 2, 3, 4, 5, 6. Okay. So -6.25, -5, and 0.6. -3, -1. -2, -0.75. -1, -1. 1 and 0.6, 2 and 0.25. Now, visually, this doesn't really mean much to me. You need to put in those asymptotes. You had a horizontal asymptote at y equals 0. You had a vertical asymptote at x equals 0. And you had a vertical asymptote at x equals -4. Now, if it does help, you could look at the actual graph to see if it helps visualize what the heck is going on here. But what they have on my graph, that's what we have here. We just have to exemplify it like this. Nice. That's what we have to worry about. That's all that this graph is. That's all that we have to do. Identify your asymptotes, identify if there are any holes, table of values, graph the thing out. Again, the actual video lesson on this was much, I don't say much easier to follow, but that's what we got. Let's try one more non-basic. Sorry. I had gotten a few emails while I was speaking. I was just making sure that there wasn't anything of immediate importance. Let's see what we got here now. Let's try one more non-basic. There we go. X squared minus 9 over x squared minus 5x minus 24. My immediate desire and hope is to factor the top and bottom of this fraction. The top of the fraction becomes x minus 3x plus 3. The bottom of the fraction becomes an x minus 8x plus 3. And if you notice, the x plus 3's cancel, which indicates that there's going to be a hole. If something like that cancels, you set it equal to 0, the x plus 3, set it equal to 0 and solve. If you do that, you get a hole at x equals -3. Now, we'll deal with that hole in a little bit, but that hole, -3, is going to show up as an error in my graphing calculator table of values. Let's look at the rest of it, though. The rest of it is x minus 3, x minus 8. Vertical asymptote. You set the bottom of that fraction equal to 0 and solve. Now, the negative 3 doesn't matter anymore. It's gone. But the x minus 8 produces an x equals 8 as a vertical asymptote. Horizontal asymptote. You take the leading term divided by the leading term. X squared over x squared just becomes a 1. You get a horizontal asymptote at positive 1. You could do x-intercepts if you wanted to. You totally could. I mean, you would get positive 3, but that's not necessary. We could go directly to the graphing calculator at this moment. It's good to type in the original. It's good to type in the original. Now there's that error at negative 3. We should also have an error at positive 8. Yeah, well, we do. It's good to get a couple of points to the left and a couple of points to the right. For the whole, I'm just going to do 1 to the left and 1 to the right. That would be sufficient. And for this one, I'm going to go... I could put this one here if I wanted to. I could go 6, negative 1.5, 7, negative 4, 9, comma 6, and 10, comma 3.5. Good. That should be sufficient. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. 3.5, there we go. 5, 6. Put that point there. 1, 2, 3, 4. 1, 2, 3, 4, 6, 7. Negative 4. 6, negative 1.5. Negative 2.5. Negative 4.58. That's weird. We'll deal with that in a minute. That's where the hole's going to be. Let's put that vertical asymptote. And you can see these things are going to be curving like they should. There's the horizontal one at y equals 1. Now this is going to be strange because this thing is basically going to flatten out like this. But there's going to be a hole right there. That's where that hole's going to be. At negative 3. And we found that out right at the beginning of the problem. If you go to the graph of this, you can see that it does give us exactly what we thought it would be. Then when we go negative 2, negative 3, oop, there's the hole. You can see there's no y value. That's what these problems basically do. You have to factor, cancel out if you can, identify any holes, identify vertical and horizontal asymptotes according to the rules outlined in the lesson, table of values, wrap that thing out. I want to wrap up this review. With 8.6. I had skipped 8.5. Solving rationals. Let's start with something like this. Now, solving this case, yes, you are going to get x by itself. But we got to destroy all those fractions. We have to destroy all those fractions. First, see if you could factor anything. Nothing can be factored for this particular problem. That 6 is over 1. But I'm going to multiply through by a least common multiple of the denominators. The 1 doesn't matter. 3 and x minus 2 have nothing in common. I'm going to multiply both the left and right side of this problem by 3 times x minus 2. If you multiply both sides by the same thing, you keep it balanced. and you don't really change the value of the problem or the value of the answer. You just change the way things look. This is a common thing that you did back in middle school. If you had to solve problems with a ton of fractions in them, you would destroy all the fractions, multiply through. Multiplying by the first fraction cancels out the 3, leaving you with a 1 times x minus 2. The 1 doesn't do anything. I'm just writing it for the sake of writing it. And in the second fraction, the x minus 2's will cancel, leaving you with 12. 4 times 3. And in the third fraction, nothing cancels, leaving you with 18 times x minus 2. Now, yes, I'm going to have to distribute that 18. And this 1 doesn't do anything. So I'm just going to write it out like this. Now I'm going to have to bring some x's to one side and numbers to the other. I'm actually going to bring the x over here. And I'm going to add the 36 over here. So this really should be, this is really strange, 46 equals 17x. That's ridiculous. We're going to get a terrible answer. No. Let's see if it actually does work, though. Let's double check our work. I wrote it down correctly. We multiplied through. The x minus 2, so there the 3 was gone. Became plus 12. Became 18 times that. 18, 18. 18 times 2 is 36. Subtract the x. Negative 2 and 12 make 10. 10 and 36 make 46. Add that over. Yeah. This problem, as terrible as it looks, has this as an answer. You can always double check your answer. Let me actually do it like this. 46 divided by 17. Let me store that to A for answer. Let's see if it works. 1/3 plus 4 divided by answer minus 2. Get you a 6 right on the dot. That's ridiculous. But it works. That's a crazy problem. Let's try another one. Now again, my first step is always going to end up being to factor if I can. In this problem, I can totally factor the bottom right fraction. There is a pretty good chance that it should factor into these two terms. In fact, you can even see it here. Yep, x plus 5, x minus 3, they multiply to negative 15, add up to positive 2. Since they do, that denominator is exactly what you want to multiply through by. Finding the least common denominator, multiplying both the left and the right side of the problem. If you multiply by the first fraction, the x plus 5's will cancel, leaving you with 6 times x minus 3. In the second fraction, the x minus 3's will cancel, leaving you with, don't forget that minus sign, 3 times x plus 5. And in the third fraction, they both cancel, leaving you with the 6. I'm going to distribute. Don't forget again that that is a negative that you are distributing. Combine some like terms. What is that, 33? That's ridiculous. Add the 33 over. You end up with x equals 13. Now, this answer should work. If I were to plug this answer back into the original problem, it should absolutely work, and I will check that in a moment. But there are two answers that would not work. There are two numbers that if you got them as answers, they would be considered false solutions. And that would be negative 5 and positive 3. Because you are not allowed to get 0 in the denominator. That would cause a vertical asymptote, and it would not be allowed to exist. So let's just test it with the 13. 6 divided by 18, because I plugged the 13 in, minus 3 divided by 10 gets me that decimal. Let's plug the 13 into the other problem. Parentheses 13 squared plus 2 times 13 minus 15. Gets me the exact same decimal. That just proves that I have the correct answer. That just proves that the answer that I found is indeed what it says it is. Let's try one more problem today. I'm going to wrap up today's review. With the following problem. Let's try 4 over 2x minus 3 plus x over x plus 1 equals negative 8x over 2x squared minus x minus 3. Double check. Make sure I wrote that down correctly. Yes, we're good to go. Again, there's a fairly good chance that these two denominators are indeed what this factors into. You can check it. It does indeed work. Anyway. I'm going to multiply through the entire thing by 2x minus 3 and x plus 1, because that is the common denominator that we were looking for. The first fraction, the 2x minus 3's will cancel. In the second fraction, the x plus 1's will cancel. And in the third fraction, they will both cancel. I'm going to have to distribute. Nope, that's a plus. And I'm losing my mind. There it is. Combine some like terms. Get one side equal to 0. Because I have a quadratic that I have to solve. I'm going to get 2 answers here. Again, Tucker method, A times C, magic numbers, the whole deal, T-chart. If you did this correctly, I believe that you should be getting something like this. Yeah. Let's double check and make sure it works. 2x squared, 8x, 1x, 4. Yep. Giving you an answer of negative 1/2 and negative 4. Now, both answers should work, and I'm going to plug them in a moment to show that they do. But there were 2 answers that we were not allowed to get. Positive 3 over 2 and negative 1. If we did, then it would force the denominators to be equal to 0. Let's just see that they do work. 4 divided by 2 times negative 0.5 minus 3 plus negative 0.5 divided by parentheses negative 0.5 plus 1. The left side gets me a negative 2. Here's the right side of the problem. Negative 0.5 minus 3. Yep. The negative 0.5 absolutely does work. Again, this is not a necessity to double check your answers, but you can if you want to. Let's try the negative 4. Left side gets you that crazy decimal. Looks wonderful. Right side. Get you the exact same decimal. It just proves that both answers do indeed work. If one of them forced a denominator to be equal to 0, then you would have to label it as a non-answer, a false solution, an extraneous solution. But otherwise, there we go. Now, I will have other things for you to review throughout the week in preparation for this major assessment. But in the meantime, that's what we got. If you have any questions, make sure you are emailing me. That is all.